In this video, I'm going to work through the method of variation of parameters applied to the other differential equation that we solved in class on Wednesday, so that you have another example of this. And I'll also try here to explain again why this method works, but ultimately, we don't do the derivation of the method every time we use it. We just sort of hit the points 1, 2, and 3 as we go through. But it is worthwhile to pay a little bit of attention to where it comes from, because that gives us some insights in where else we might apply this idea. Okay, so the differential equation here is y prime plus 3y equals 4y, equals 4, sorry. So here's our differential equation that we're going to solve. The complementary equation, meaning the homogeneous version of that, is the same thing with a 0 on the side. And I won't walk through the reason, because we did that last time, but one solution to that is y1 equals 3 to the minus 3x. So that's just from that process of rewriting that equation as y prime over y equals minus 3, and then kind of follow through from there. So we won't work through that. And so that's step one. So good for us. We did step one. The second step is, the logic is basically this. This y1 is not the solution to the original differential equation, but it's a solution to something that's close to it. And so we're hoping that maybe some variation on this, if we add something to this, it will then solve the original one. So this solves something close, and so we want to think, how could I modify that to solve the original? And so the modification that we try is to just multiply it by something. So suppose multiplying y1 by some function u provides a solution to the original equation, the non-homogeneous equation. So that means, and this is the part where I'm showing the derivation of the idea, we could just skip right to what step 2 says, but here's how it works. That means that in this equation, the equation that I have here mentions y prime plus 3y, and so I can build that. The y prime, is going to be the product rule applied to this form that I know my y prime has, and my y has. So if I know y has this form, then y prime from the product rule is u prime times y1 plus y1 prime times u. And then plus 3y, but again, y is u times y1. So that's what y prime plus 3y looks like if this construction is a solution to my original equation, and the original equation tells me that that should be equal to 4. So the original equation is telling me that y prime plus 3y is 4, and I know from substituting that y prime plus 3y is this stuff. So the main reason this works is because we can rearrange these terms a little bit, and so this is just rearranging the terms. I'm not going to do anything to it here. I'm going to leave that u prime times y1 where it is, and then I'm going to group these other two terms because the other two terms have a u in it. So I'm going to factor the u out and write down the other stuff that I have. Oh, there's missing a 1 there. Sorry. So all I've done from one line to the next there is just regroup the parentheses and factor a u out of those second terms. The reason that matters is that, remember, y1 was a solution to the homogeneous equation, and so this is 0. y1 prime plus 3y1 has to be 0. That's what we said here. This was a solution to the homogeneous equation. So that function plugged into that homogeneous equation gives me 0, and so that part is 0. So this part's gone. And so what I'm left with is just the 4 that's on the left-hand side, and u prime times y1 on the right-hand side. But remember, I know what y1 is. y1 is e to the minus 3x. So this is where what I'm ending up with. And so that means I know that u prime, and I'm not going to divide both sides by e to the minus 3x. That's weird. I'm going to multiply both sides by e to the positive 3x. So u prime will be 4 times e to the positive 3x. So that's just an antiderivative problem. So if u is 4 times e to the 3x, then if u prime is that, then u is 4/3 e to the 3x. We get that factor of 1/3 coming outside, plus a constant. And so now I have my y1 up here, I have my u right here, and remember we set all this up so that the product of u times y1 is a solution. So there's a lot of little pieces I have to put together, but once I locate all of them, this guy, and this guy, all together tell me that y is the product of u and y1. So that means the product of 4/3 e to the 3x plus c times y1, which is e to the minus 3x. And I can multiply that e to the minus 3x through, and I'll get y is 4/3 plus c times e to the minus 3x. And that's exactly what we got before when we used the integrating factor method. So you can go through the process here, and you can see all these pieces coming together. The solution of the homogeneous equation was straightforward. This resulting u prime equation, that's right here. Put a little cloud around it. So that thing with a little bubble around it was my original f of x, which was just the number 4 in this case, divided by my y1. So that's what this is. So that's the original f of x, and this was what I get when I divide by y1. Then that becomes an antiderivative problem to find u, and then I can put it all together. So I hope that helps to see it again. I know it's hard to follow when I have my small tablet and I have to kind of squish my writing together instead of spreading it out. I would recommend you take a piece of paper and try to write it out so that all the pieces don't lay on top of each other. And I think you'll see it better if you do it that way. Hopefully you can follow the video and sort of lay out your own organization of the solution method.